Obhiraj, roll number 1027. You become a presenter. Please don't do these type of things. Please return it to its previous position, as I am the presenter. I am asking again, Obhiraj. Obhiraj, roll number 1027. Okay, good morning, everybody. Can you hear me? Is my voice is audible to you?
Yes, sir.
Yes, sir. Yes.
Okay. So let's start. Today we want to start a new module, series solution of ordinary differential equation. Okay. The complex part, the module of complex part has been done. Now we will start the ordinary differential equation, and the topic is series solution of ordinary differential equation. Now in the last semester in differential equation class, we have mostly solved ordinary differential equations with constant coefficients. Constant ordinary differential equation with constant coefficients means the coefficients of dependent variables and its derivatives are constant. Okay, here this is a typical example. This is a typical example of a ordinary differential equation with constant coefficients. You can see that the coefficients of y, dy dx, d2y dx2, that is the dependent variable, and its derivatives, that is the coefficients of dependent variables and its derivatives, are constants. Okay, in last semester we have mostly solved this type of equations. Now we have solved ordinary differential equation with variable coefficients in the last semester. Obhiraj, again I am telling you, don't do this type of things. Okay, let's start. We have also solved Cauchy-Euler equation, which is a special type ordinary differential equation with variable coefficients. Whenever comes to differential equation with variable coefficients, we have only solved one type of differential equations with variable coefficients, and this type is named as Cauchy-Euler equation. A typical example of Cauchy-Euler equation is this. We have already done it in the last semester. What we do to solve a Cauchy-Euler equation? To solve a Cauchy-Euler equation, we put x equal to e to the power t or t equal to log x. And by putting this, we reduce the given equation with to an ordinary differential equation of constant coefficients. See, Cauchy-Euler equation
স্যার ভয়েস
Cauchy Euler
আসছে না
equation is a
আটকে
ordinary
যাচ্ছে
differential equation.
স্যার ভয়েস আটকে যাচ্ছে এই পার্টটা
সবার কি
আরেকবার একটু বলুন না হ্যাঁ হ্যাঁ আটকে যাচ্ছে আমার আটকে গেছিল এখানটা
सर आवाज नहीं आ रहा ठीक
Okay, let's try. So we have solved in the last semester. We have mostly solved differential equation with constant coefficient. We have solved a special type of ordinary differential equation with variable coefficients, and this type of equations with variable coefficients was named as Cauchy-Euler equation. Typical example of Cauchy-Euler equation is given in this box. Okay, you can recall that this type of Cauchy-Euler equation has been solved in the last semester. Now, how we have solved this Cauchy-Euler equation? We have put x equal to e to the power t or t equal to log x and reduce the equation to an ordinary differential equation of constant coefficient. Okay, Cauchy-Euler equation is an ordinary differential equation with variable coefficients. That is, the coefficients of y, dy, dx, d2y, dx2 are variables, not constant, are variables, function of x. See in the typical example, here the coefficients are x square, x, and so on. That is the variables. Okay, now putting x equal to e to the power t or t equal to log x, we reduce this equation to a ordinary differential equation of constant coefficient. If you can recall, we by putting x equal to e to the power t, we reduce this type of Cauchy-Euler equation to a equation of constant coefficients. Then we solve the ordinary differential equation with constant coefficients. Okay, we know how to solve the ordinary differential equation of constant coefficients. So by the procedure, we solve this equation with constant coefficients. Finally, we have a solution of that equation of constant coefficient. And finally, again substituting x equal to e to the power t or t equal to log x in the solution, we find the solution of the given differential equation. Okay, so in the Cauchy-Euler equation is an equation which can be reduced to an ordinary differential equation of constant coefficients. I am repeating again. Cauchy-Euler equation is such type of equation which can be reduced to an equation of constant coefficients. Oviraj, if next time it is done, I will take action against you, okay?
Sir, he might not be the real Abhiraj. Maybe someone is using his name by making fake account.
So how someone got this meeting ID?
না ক্লাসেরই কেউ করছে হয়তো ক্লাসেরই অন্য কেউ করছে
তোমাদের
হয়তো
ব্যাচে এই
এটা
সমস্যাগুলো
অভিরাজ
কেন
নয়।
হয় বলো তো? তোমাদের ব্যাচে এই সমস্যাগুলো কেন হয় বলো তো? আমি তো আরো দুটো ফার্স্ট ইয়ারের ব্যাচে ক্লাস নিই, কোথাও তো এরকম ধরনের সমস্যা হয় না আমার।
স্যার কি করে বলবো বলুন তো এটা
Okay, let's start again. So Cauchy-Euler equation was that type of equation which can be reduced to an equation of constant coefficients. But if we are given an ordinary differential equation of variable coefficient which is not reducible to a differential equation of constant coefficient. Okay, if we are given
Sir?
ordinary differential equation which is not reducible to a differential equation of constant coefficient, then how to solve this? In this case, we look for a series solution of the given differential equation by assuming a power series type solution of the dependent variable. Okay. So whenever a differential equation with variable coefficient is reducible to a differential equation of constant coefficients, then it is okay. Then we can solve it. But when a given ordinary differential equation of variable coefficient is not reducible to a differential equation of constant coefficient, then what happens? Then we look for a series solution of that differential equation. Okay, that is why series solution of ordinary differential equation is important. So it is important to solve those equations which are of variable coefficients, and those equations are not reducible to a equation of constant coefficient. Okay.
सर एक बार वापस स्क्रीन
Yes.
शेयर करिए ना, मेरे को शो नहीं हो रहा है स्क्रीन।
ठीक है,
तो मुझे भी शो नहीं हो रहा।
स्क्रीन शेयर करिए ना एक बार वापस से।
screen तो already shared.
नहीं सर, शो नहीं कर रहा है।
नहीं हो रहा
বন্ধ করে
স্যার।
আরেকবার করুন,
দেখাচ্ছে না স্যার।
স্ক্রিন শেয়ারটা বন্ধ করে
ঠিক আছে।
আরেকবার করুন।
এখন ঠিক আছে? Now it is.
না স্যার আসেনি।
I have shared the screen again. Okay, can you see it?
नहीं
না স্যার
नहीं आ रहा।
ও
আসেনি,
স্যার
সেটিংসটা চেক করে নিন।
Then it is a network issue, I think. Nobody cannot can see it.
ও স্যার।
না
नो
স্যার,
सर।
তাহলে স্যার আপনার নেটওয়ার্কে মনে হয় প্রবলেম হচ্ছে।
কেউ দেখতে পাচ্ছ না?
না স্যার,
না
কেউ দেখতে পাচ্ছে না।
দেখতে পাচ্ছি না।
ওকে, again আমি স্টপ শেয়ার করছি।
স্যার অভিরাজ বলছে, এটাই তো বলছিলাম স্যার, কতক্ষণ ধরে আমারও গ্লিচ হচ্ছে।
তুমি বারে বারে তোমাকে নিজেকে প্রেজেন্টার করে দিচ্ছ কেন? আমার সঙ্গে
স্যার
তো
গ্লিচ
screen
হচ্ছে তো স্যার, কি করবো স্যার, এটা তো
হ্যাঁ?
গ্লিচ হচ্ছে স্যার, নেটওয়ার্ক ইস্যু হয়ে যাচ্ছে স্যার।
আচ্ছা, এবার দেখা যাচ্ছে?
नहीं सर।
सर मैं स्क्रीन शेयर कर दूं क्योंकि मैंने स्क्रीनशॉट ले लिया था उसका।
स्क्रीनशॉट से तो नहीं होगा, तो पीडीएफ फाइल है, उसके बाद का पेज भी जाना है।
স্যার আপনি না হলে শেয়ার থেকে ইয়াটা পিডিএফটা পাঠিয়ে দিন, তো তারপর আমাদের কেউ না হয় একজন শেয়ার করে দেবে স্ক্রিনটা।
ঠিক আছে, আমি তমজিৎকে পাঠিয়ে দিচ্ছি। এখনো দেখা যাচ্ছে না? কেউ দেখতে পাচ্ছ না?
হ্যাঁ স্যার, আমি একটা কাজ করছি, আপনি যেটা
হুম,
পাঠিয়েছেন না, ওটা আমি তাহলে করছি, শেয়ার কন্টেন্ট করছি।
শেয়ার
আচ্ছা,
করুন না
আমি
তাহলে
আরেকবার
তো হবে।
ট্রাই করে দেখি, একবার ট্রাই করে দেখি আরেকবার,
হ্যাঁ হ্যাঁ
তারপরে
করুন
দেখি।
করুন।
এবার দেখা যাচ্ছে কি?
নো।
सर नहीं दिख रहा।
না আনসার। আমি তাহলে ইয়ে করি,
সমস্যা
এটা শেয়ার করি।
ঠিক
হ্যাঁ
আছে।
তুই স্ক্রিনটা শেয়ার কর না।
হ্যাঁ। আনসার। হ্যাঁ স্যার, দেখতে পাচ্ছেন?
হ্যাঁ।
আরে তুই দমজিৎ,
হ্যাঁ।
তুই তোর ফাইল থেকে খোল পিডিএফটা, তাহলে দেখ ফুল স্ক্রিন পাবি।
ফাইল থেকে
আমার ফাইল
খুলবো
থেকে
সেটা।
কোনো অপশন নেই। দেখ না, অসুবিধা কি আছে? পুরোটাই তো আসছে।
হ্যাঁ হ্যাঁ
হ্যাঁ আসছে। হ্যালো।
Okay, go to the next page.
হুম।
Okay. Now consider the, let's start from here. Now consider the differential equation. This is the differential equation. Let me annotate, okay, if I try to.
Yes.
Now consider the differential equation this. d2y dx2 plus px dy dx plus qxy equal to 0. Here px and qx are functions of x only. Okay, these are not constants. Consider this equation d2y dx2 plus px dy dx plus qxy equal to 0. Here px and qx are functions of x only. These are not constants. So it is a differential equation with variable coefficient. Here most important thing is to find the nature of the functions px and qx of equation 1. Okay, then by means of nature, by the word nature we mean that we have to check that whether the functions px and qx are analytic at a certain point x equal to 0, x equal to x0 or not. Okay, by means of the nature of px and qx, we actually want to find that whether at a certain point x equal to x0, the functions px and qx are analytic or not. Okay, so let us elaborate it through an example. So consider the ordinary differential equation this. Okay, d2y dx2 plus x squared dy dx plus e to the power xy equal to 0. Now compare this differential equation with this standard form of differential equation with the given equation 1. Okay. Now by comparing the given differential equation with this differential equation, we get px equal to x square and qx equal to e to the power x. See, this is here px is the coefficient of dy dx and x squared is the coefficient of dy dx. So px equal to x square and qx is the coefficient of y in the standard equation, and here qx is e to the power x is the coefficient of y. So qx is e to the power x. Now px equal to x square. So it is a polynomial function and polynomial functions are analytic everywhere. And qx is the exponential x. Exponential functions are analytic everywhere. So px and qx are analytic everywhere at any point x. Okay. Now again we consider this equation d2y dx2 plus 1 by x dy dx plus x square minus m square by x square y equal to 0. Okay. Now comparing this equation with the standard form. With the standard form, we see that here px equal to 1 by x and qx equal to x square minus m square by x square. Okay. Here we have taken this equation. Now we compare this equation with the standard form, that is the equation 1, and by comparing we get px equal to 1 by x and qx equal to x square minus m square by x square. Okay. Now Tamanjit, go to the next page. Okay. So let me write. Singular point where the points are not analytic, you already done. So if I write px equal to 1 by x minus 0 and qx equal to 1 by x minus 0 whole square, then px and qx both are not analytic at the point x equal to 0. In fact, x equal to 0 is a singular point of the functions px and qx. Now up to this point, if anyone has a problem, you can ask me. Okay, I think no problem. So let me give some formal definitions of ordinary point and singular point. Now first we considered the ODE, the standard form of the ODE, d2y dx2 plus px dy dx plus qxy equal to 0. This is the standard form of the ODE. Now what is ordinary point? Ordinary point, we give the definition of ordinary point. A point x equal to x0 is called an ordinary point of the ordinary differential equation 1. This is the ordinary differential equation 1. So a point x equal to x0 is called an ordinary point of the ODE 1 if both px and qx are analytic at x equal to x0. So if both px and qx are analytic, both, you can, I am again saying both. If both px and qx are analytic at the point x equal to x0, then the point x equal to x0 is called an ordinary point of the given or ordinary differential equation. Now let me say what is singular point. A point x equal to x0 is called a singular point of the ordinary differential equation 1 if at least one of the functions px and qx is not analytic at x equal to x0. Okay. So when px and qx are both analytic, then at x equal to x0, then x equal to x0 is an ordinary point. But if any one of the function is not analytic at the point x equal to x0, if any one of the functions px and qx is not analytic at the point x equal to x0, then the point x equal to x0 is called a singular point. I am repeating again. If both the functions px and qx are analytic at the point x equal to x0, then the point x0 is called a ordinary point. But if any one of the functions px and qx is not analytic at the point x equal to x0, then x0 is said a singular point. Okay. Now singular point can be of two types. The singular point is of two types. The first one is regular singular point and the second one is irregular singular point. Singular point is of two types, regular singular point and irregular singular point. Now what is regular singular point? A singular point x equal to x0 is called regular singular point if both x minus x0 into px and x minus x0 whole square into qx are analytic at the point x equal to x0. Okay. The function px may not be analytic at the point x equal to x0, but to be a regular singular point, the function x minus x0 into px should be analytic at the point x0. Again, the function qx may not analytic at the point x equal to x0, but to be a regular singular point, the function x minus x0 whole square qx should be analytic at the point x equal to x0. That is, to be a regular singular point, these two functions x minus x0 into px and x minus x0 whole square into qx should be analytic at the point x equal to x0. Okay. And what is irregular singular point? Irregular singular point means if any one of the functions x equal to x0 px or x equal to x0 whole square qx is not analytic at the point x equal to x0. A function to be a irregular singular point, at least one of the functions x minus x0 px or x minus x0 whole square qx should be analytic at the point x equal to x0. So up to this point, if anybody has a problem, you can ask me. কি হলো তমজিৎ?
স্যার একটু দাঁড়ান। হ্যাঁ স্যার, পাচ্ছেন?
এবার দেখতে পাচ্ছি। ঠিক আছে, পরের পেজে চলো। Okay, let me elaborate this whole thing, this ordinary point, regular singular point, irregular singular point by the following example. We are going to an example. So this is an example. So this is an example. The given differential equation is 2x squared d2y dx2 plus 7x into x plus 1 dy dx minus 3y equal to 0. We want to find the ordinary point, regular singular point or irregular singular point of the given equation. Okay. So the given equation
স্ক্রিন
is
দেখা যাচ্ছে না আবার।
দেখা যাচ্ছে না?
না
হ্যাঁ স্যার, একটু দাঁড়ান,
দেখা যাচ্ছে।
একটু দাঁড়ান স্যার, আমি জাস্ট একটু এরোপ্লেন মোডটা অন করে দিই, তা নাহলে কল আসছে। হ্যালো, হ্যাঁ স্যার, হ্যালো।
Okay, huh.
Hmm.
So let me
Yeah.
elaborate this whole or this ordinary point, singular, regular singular point, irregular singular point by an example. Okay. So this is a approve request. Okay. So this is a or given ordinary differential equation with variable coefficient. So 2x squared d2y dx2 plus 7x into x plus 1 dy dx minus 3y equal to 0. Okay, now the step one is we write the given equation in the form of the standard equation. The standard equation was d2y dx2 plus px dy dx plus qx equal to 0. And that is, in the standard equation, the coefficient of d2y dx2 is 1. But here in the given equation, the coefficient is of d2y dx2 is 2x square. Okay. So we have to divide the given equation by 2x square in both sides. Okay. So step 1 is to we make the given equation, we write the given equation in the standard form. The standard form is d2 by dx2 plus px dy dx plus qx equal to 0. Okay. To do so, we divide the given equation by 2x square in both sides. So dividing 2x square in both sides, we get equation 2. Okay. Now this is a simple calculation. I think that is not very difficult to understand. So what we have done, we have divided the given equation by 2x square and got equation 2. This is in the standard form. This equation 2 is in the standard form. Now comparing this equation 2 with the standard form, comparing the equation 2 with this standard form, comparing it with the standard form, we get px equal to 7 into x plus 1 by 2x and qx equal to minus 3 by 2x square, right? So we compare the equation 2 with the standard form of equation, and we get px equal to 7 into x plus 1 by 2x and qx equal to minus 3 by 2x square. Okay, so this was the step 2. Step 2 is compare the given equation with the standard equation and find px and qx. So by comparing the given equation with the standard equation, we have found px and qx. Now step 3, find the singular point, that is figure out the points at which px and qx are not analytic. Now see, at px there is in the denominator of px there is 2x, that is 2 into x minus 0, and in the denominator of qx there is x square, that is 2 into x minus 0 whole square. So at x equal to 0, the px and qx are not analytic. So x equal to 0 is a singular point. Okay. See, px and qx are not analytic at x equal to 0. So x equal to 0 is a singular point. Now clear? Up to this point, if anybody has problem, you can tell me. So no problem. So we have found x equal to 0 is a singular point. Now we have to check that whether x equal to 0 is a regular singular point or irregular singular point. So we are going to check whether x equal to 0 is a regular singular point or irregular singular point. Antamajit, go to the next page.
That's
Okay. So now we find that whether x equal to 0 is a regular singular point or not. Okay. So for this case, we have to find the two functions x minus x0 px and x minus x0 whole square qx. Okay. Now here x0 is equal to 0. X equal to 0 is the singular point. X0 is the point where the function is where the functions are analytic or not. So here x0 is 0. So x0 is 0. Since 0 is the singular point, so we have to find x minus 0 px. We have to find x minus 0 px. So x minus 0 px means x into px, that is x into what is the value of px, 7 into x plus 1 by 2x. So x minus 0 px ultimately 7 by 2 into x minus x plus 1, which is a polynomial function. So x minus 0 px becomes 7 by 2 into x plus 1, which is a polynomial functions, and polynomial functions are analytic everywhere. So x minus 0 px, this function is analytic everywhere. So this function is analytic at x equal to 0. Now second, we have to find x minus x0 whole square px. So it's become, since x0 equal to 0 here, so x minus 0 whole square qx. So this is x square qx. So x square into what is the value of qx? The value of qx was minus 3 by 2 x square. Okay, so we have put the value of qx there. So finally, x minus 0 whole square qx becomes minus 3 by 2, which is a constant. Since it is a constant, therefore it is analytic everywhere. So the functions x minus 0 whole square qx is also analytic at x equal to 0. So what we have find? We have find the function x minus 0 px is analytic at x equal to 0, and x minus 0 whole square qx is analytic at x equal to 0. Therefore, the point x equal to 0 is a regular singular point of the given differential equation. Okay. So what we find? We have found that x equal to 0 is a singular point of the given differential equation. Next, we want to show that whether this x equal to 0 is a regular singular point or irregular singular point. Now we find x minus 0 px. Now x minus 0 px is a polynomial function, so it is analytic at x equal to 0. Then we find x minus 0 whole square qx, which is a constant, so it is also analytic at the point x equal to 0. So at the point x equal to 0, the functions x minus 0 px and the function x minus 0 whole square qx both are analytic. Therefore, x equal to 0 is a regular singular point of the given differential equation. Okay. Any problem up to this point?
Yes, sir.
No problem, I think. Any problem? You can ask me. Okay, Tamajit, go to the next page then. Okay, here is another example. Here we have to show that x equal to 0 is an ordinary point of the given ODE. Okay, here we have to show that x equal to 0 is an ordinary point of the ODE x square d2 by dx2 plus x sin x dy dx plus 1 minus cos x y equal to 0. Okay, so step 1 is to write the given equation in the standard form, that is d2 by dx2 plus px dy dx plus qxy equal to 0. So to do so, we have to divide the equation by x square. So by dividing the given equation by x square, we get this equation, this d2y dx2 plus x sin x by x square dy dx plus 1 minus cos x square by y equal to 0. And after a simplification, we get this equation 1, that is dy dx d2y dx2 plus sin x by x dy dx plus 1 minus cos x by x square y equal to 0. Okay, now this is my equation 1. This is the equation 1. Now comparing this equation, next step is to compare this equation with the standard equation to find px and qx. So we compare equation 1 with standard equation d2y dx2 px dy dx plus qxy equal to 0, and we get px equal to sin x by x and qx equal to 1 minus cos x by x square. Okay, now we have to check that whether these px and qx are analytic at the point x equal to 0. So we have found px is sin x by x and qx is 1 minus cos x by x square. So our next job is to check that whether px and qx are analytic at the point x equal to 0. Okay. Now see that the functions are somehow difficult here. Here px equal to sin x by x. Now if we put x equal to 0, if we put x equal to 0 in the px, we get p0 equal to sin 0 by 0. P0 equal to sine 0 by 0. Okay, that is sine 0, the value of sine 0 is 0, so this is 0 by 0. So 0 by 0 is an indeterminate form. You have uh, already read in the first semester. Recall what was indeterminate form, L'Hospital rule there. Okay, 0 by 0, infinity by infinity, those are the indeterminate form. So here when we put x equal to 0 in Px, we get sine 0 by 0, that is a 0 by 0 indeterminate form. So to see whether Px is analytic at the point x equal to 0, we take the limit x tends to 0. We take the limit x tends to 0 Px. If this limit exists, then we say that the function Px is analytic at the point x equal to 0. Okay, whenever we by putting the value x equal to 0 or x equal to something x equal to something, we get an indeterminate form. Then we find the analyticity with the help of limit. Okay, here we put x equal to 0 in Px and find an indeterminate form 0 by 0. So we find the analyticity by the limit x tends to 0. If the limit x tends to 0 Px exists, if the limit x tends to 0 Px exists, then the function Px is analytic at the point x equal to 0. But if the limit x tends to 0 Px does not exist, then the function x equal to 0 is not analytic. Then the function Px is not analytic at the point x equal to 0. Okay. So here we see that limit x tends to 0 Px is limit x tends to 0 sin x by x. Now this limit, the value of sin x by x is 1. Okay. So it is a problem of limit from class 11. In any standard book of class 11, you can find the limit of, you can find that the limit x tends to 0 sin x by x equal to 1. So limit x tends to 0 Px exists. So Px is analytic at the point x equal to 0. Okay. Now again in Qx, if we put x equal to 0, then Q0 is 1 minus cos 0 by 0. That is 1 minus 0, 1 minus 1 by 0 equal to 0 by 0. Again a indeterminate form. Again a indeterminate form. So here also we will take the limit. So limit x tends to 0 Qx. So limit x tends to 0, 1 minus cos x by x square. This is a 0 by 0 form. So we use the L'Hospital rule here. What was L'Hospital rule? L'Hospital rule was we find the derivative of both the numerator and denominator. Okay. So in the next step, we find the derivative of both the numerator and denominator. The numerator was 1 minus cos x. The derivative of 1 minus cos x is sin x. So in the second step, we write sin x in the numerator. And the denominator was x square. So derivative of x square is 2x. So in the second step, we write 2x in the denominator. Now we see that this limit reduces to 1 by 2 limit x tends to 0 sin x by x. Since limit x tends to 0 sin x by x is 1, therefore it is going to be half. So the limit x tends to 0 Qx equal to half, so it exists. So we see that limit x tends to 0 Px and limit x tends to 0 Qx both exist. So both Px and Qx are analytic at the point x equal to 0. So Px and Qx, so x equal to 0 is an ordinary point of the given differential equation. Okay, any problem you can ask me. If you have find any problem up to this point, you can ask me. So no problem, I think.
স্যার ঠিক আছে।
ঠিক আছে, ওকে, তাহলে নেক্সট পেজে চলো। ওকে, okay, let me start the power series solution about some ordinary point x equal to x0. Okay, so power series solution can be done about some point. Okay, maybe it is an ordinary point. If we find the power series solution about a ordinary point, then there is a rule. Okay, there are steps. If we follow the steps, we can find the series solution. Now again, if x equal to x0 is a regular singular point, then the steps, the procedure is it is little bit different. Okay, then the steps are little bit different. By following those steps, we can find the series solution of the given differential equation. So our first topic is power series solution about the ordinary point x equal to x0. When x equal to x0 is an ordinary point, we find the power series solution of the differential equation about the point x equal to x0. Okay. So let us consider the ordinary differential equation y double dash plus px y dash plus qxy equal to 0. Y double dash means this is the second derivative of y with respect to x, that is d2y dx2. Okay, and y dash means this is the first derivative of y with respect to x, that is dy dx. And so this is the given equation. So this is nothing but d2y dx2 plus px dy dx plus qxy equal to 0. That is the standard equation. And suppose x equal to x0 is an ordinary point of the equation 1. Suppose x equal to x0 is the ordinary point of the equation 1. Okay. Now in the given problem, when you are given a problem, you will be asked that find the power series solution about the point x equal to x0. Okay. Now then in the question you will not given the information whether x equal to x0 is a ordinary point or regular singular point or irregular singular point. So in step 1, while solving the problems, in step 1 you have to find x equal to x0 is in the nature of the point x equal to x0. Okay, actually you have to find whether x equal to x0 is a regular point or is an ordinary point or regular singular point or irregular singular point. If x equal to x0 is an ordinary point, then you can use this algorithm. Okay, now we are going to find the procedure of solving a differential equation when x equal to x0 is an ordinary point. Okay, so in step 1, your job is to find the nature of the point x equal to x0. Now say x equal to x0 is an ordinary point. Then we go to step 2. Okay. In step 2, we consider y equal to this infinite series. Y equal to summation n runs from 0 to infinity an into x minus x0 whole to the power n be a solution of the given differential equation. In step 2, we consider y equal to summation n equal to 0 to infinity an into x minus x0 whole to the power n be the solution of the given differential equation. Okay, we name this infinite series equation 2. Now the infinite series looks like if we expand the summation, then this infinite series looks like y equal to a0 plus a1 x minus x0 plus a2 x minus x0 whole square plus a3 x minus x0 whole cube and so on. For n equal to 0, a0 x minus x0 to the power 0, that is 1. So a0. For n equal to 1, a1 x minus x0 to the power 1 plus for n equal to 2, a2 x minus x0 whole square and so on. Okay, so in step 2 we consider an infinite series as a solution of equation 1. Okay, now in step 3 In step 3, we find the value of y dashed and y double dashed. Okay, that is the value of the first derivative of y and the second derivative of y. Now we have considered y equal to summation, we have considered y equal to this thing. We have considered y equal to this thing, that is y equal to summation n equal to 0 to infinity an x minus x0 to the power n. Okay, now the first derivative of y will be y dash, that is dy dx. So this will be this summation n equal to 1 to infinity n the power comes to the front n x minus x0 to the power n minus 1. Since we are taking the first derivative, okay, the whenever we have n equal to n equal to 0, since the n comes to the front, so when n equal to 0, this terms goes to 0 because there is 0 into a0 x minus x0 to the power minus 1. So the first term is 0. So the summation actually running from n equal to 1 to infinity. When n equal to 0, the terms gives 0. Okay, so the actual non-zero terms comes from n equal to 1. So in this case, the summation runs from n equal to 1 to infinity. It is very important. Okay, it is very important to know that here n runs from n equal to 1 to infinity. If you can write n equal to 0 to infinity, but in that case the first term, when you write the first term for n equal to 0, there is a 0 into a0 x minus x0 to the power minus 1, so it goes to 0. So we don't write the first term, we write actually the non-zero terms of the summation comes from n equal to 1. So the summation runs from n equal to 1. Here n equal to 1. See. And in the case of second derivative, we find d2y dx2 equal to n equal to 2. Summation runs from n equal to 2 into n minus 1 an x minus x0 to the power n minus 2. Here also for n equal to 0, the terms goes to 0, and for n equal to 1, the 1 into 1 minus 1 a1, that is 1 into 0. So for n equal to 1, we again got a 0. So the actual non-zero terms comes from n equal to 2. So we write the summation from n equal to 2. Okay. So up to this point, if anybody has problem, you can ask me.
So step 2 में y equals to summation of n equals to 0 to infinity an. सर वो वाला statement कहाँ से आया?
We are considering this. Okay. This is the power series solution. The method is actually we consider a power series as a solution of the given differential equation. Okay. Then we find the solution as a sum of two power series. Okay. This is the procedure.
Okay, sir.
Okay. Here the terms an, actually here the terms an are not known. An are not known. We will find these terms in terms of two constants only. Okay, and find a solution which contains two arbitrary constants. Okay, here the solution contains n arbitrary constants, right? The terms an are not known here. See, we are considering the solution y equal to as a power series. Okay, so power series has these power series have infinite number of constants a0, a1, a2, a3, a4, and so on. Okay, but the given differential equation has a order. The given differential equation is of order 2. Okay, that is the highest order of the given differential equation is 2. So the solution of the given differential equation must contain two arbitrary constants. Okay, the solution of the number of arbitrary constants in the solution of a differential equation must be equal to the order of the differential equation. So here the order of the differential equation is 2, and the solution of the order of the solution of the differential equation must contain 2 arbitrary constants. Okay. But whenever this
Hello.
power series as a solution, we see that there are infinite number of arbitrary constants. Now our task is to reduce these arbitrary constants in into 2 arbitrary constants. Okay, we find the values of these infinite number of arbitrary constants as in terms of 2 arbitrary constants, a0 and a1 actually. Okay, that is our goal. We consider a solution which has infinite number of arbitrary constants, but we will reduce this infinite number of arbitrary constants into 2 arbitrary constants by finding the values of those constants. Okay, this is my goal. Now tell me, if anybody has problem, you can again ask me. অমৃত কি হলো? হ্যালো, can anybody hear me?
Yes, sir.
হ্যাঁ, তমজিৎ স্ক্রিন কোথায়?
হ্যালো।
হ্যাঁ, আমি স্ক্রিন দেখতে পাচ্ছি না। তমজিৎ, হ্যালো, তমজিৎ, can you hear me?
Hello, sir.
Yes, who is it?
Rajrupa, sir.
Okay, Tomojit was sharing the screen. Where is he?
Wait, sir. I guess there is some network problem. Even I cannot see any screen. Wait for some minutes, I guess.
Okay, let me share this document again. Can you guys see the PDF now?
Yes, sir.
Okay, so
আচ্ছা।
Okay. So we have found the values of y dashed and y double dashed from step 3. Okay. Now in step 4, our job is to put these values of y double dashed, y dashed and y in the given differential equation. Okay. So we get, by putting those values, we get this equation. Now in step 5,
Hello. Sound
hello.
আসছে না,
Hello. Now in step 5, we equate to 0 the coefficients of x minus x0 and find the coefficients a2, a3, a4 in terms of a0 and a1. Okay. In fact, to find this, to equating the 0, the coefficient of x minus x0 to the power n, we get a recurrence relation. Okay. And from that recurrence relation, we get the values of a2, a3, a4 and so on in terms of a0 and a1. Okay. And in step 6, we put these values of a2, a3, a4 and so on in the in equation 2, that is in the solution we have considered earlier. Okay. In the solution was y equal to this, that is a0 plus a1 x minus x0, a2 x minus x0 whole square, a3 x minus x0 whole cube and so on. And here we write the values of a2, a3, a4, a5, a6 and so on in terms of a0 and a1. So we finally get a0 into infinite series plus a1 into an infinite series. We name this infinite series as phi x and psi x. Okay, so we get y equal to a0 into phi x plus a1 into psi x. So this is the solution of the given differential equation where a0 and a1 are arbitrary constants. Okay. Now I know there is a lots of ambiguity. What is the recurrence solution? How can we find the values of a2, a3, a4 in terms of a0 and a1? Okay, there will be lot of questions. Okay, from step 5. From step 5 to step 6, there will be a lot of questions. Okay, those questions will be answered while solving a problem. Okay, it is not possible to answer this theoretically. You will be answered those questions while we will solve a problem. Just now remember what are the steps. Okay, just remember what are the steps to solve the problem. Whenever we solve the problem, these ambiguities will be resolved. Okay, you will find the similarities of the step and the procedure of finding the problem, solving the problem, right? So today I am terminating here. It is 12:07. 1 hour has been done. So from the next day, in the next day, we will go for a problem, that is the following problem, and we will solve this about the point x equal to 0. Okay, and then most of the ambiguities will be resolved, right? Okay, so let me end the meeting. Any question you have? No questions?
No,
Okay,
sir.
thank you everybody. Let's end the class.